Hello and welcome to our series of PYB 350 lecture overviews. Today I'm going to take you through t-tests in a nutshell. So just before we start, let's just remember a few of the basics. Okay, going back to simply what our x or our y means, and I'm going to introduce you to a little bit of notation that we're going to need as we go through into our more complex designs in 350. So X or Y, depending on the textbook you're using, with a little notation at the bottom of it, just means the ith score on the dependent variable. Yeah. So M or X bar or Y bar is simply the mean of a set of scores. And if we add our little notation to it, it just means the mean for the jth group. Okay, so we can have the ith score in the jth group and the mean of the jth group. If we have the little notation t to the bottom of it, it just simply means our grand mean or total mean of the whole experiment. Okay, remember, little n is the number of scores in a particular group or cell. Big N is the number of scores in our whole experiment. And again, if we use our little annotations here, Nj is just simply the number of scores in the jth group, in group J. And finally, our fundamental building block for all of the stats that we do, our sums of squares. Remember, that is just how far each individual score is away from the group mean, squared to get rid of the sign, and summed for each individual. Okay, just a quick reminder of our key distributions then. We have our population of interest from which we draw our sample. And then our actual statistics are based on our distribution of sampling means. That is, if we took an infinite number of samples from our population and plotted their mean, we would have a distribution of sampling means. And this is our comparison distribution for the majority of our statistics. So remember, each one of these distributions has a mean, variance, and a standard deviation. Okay. The standard deviation of our distribution of sample means is known as our standard error, or in other words, the amount of error we can expect when we're using our sample mean as a prediction, or as an estimation, I should say, of our population mean. Okay, so remember back to the logic of hypothesis testing. What we're simply trying to do is decide whether our sample statistic belongs to the null hypothesis comparison distribution, that is the distribution where the IV has had no effect, or if it's such an extreme score that it's more likely that it's come from our research or our alternative hypothesis, where our IV has had an effect. And remember, we usually set our cutoff levels at the point where there are less than 5% scores in the extreme tail there. So, of course, every time we make a decision, it is based on probability, and therefore we have a chance of making an error. So, if our score falls beyond our cutoff point, which we've usually set at an alpha level of 0.05 in psychology, but in fact it was simply an extreme score, and it does actually belong to our null hypothesis distribution, we've made a type 1 error, the probability of which is whatever we set our alpha level at. So in this case, 5%. Of course, our score could fall just the other side of the cutoff. Therefore, we do not reject the null hypothesis and we say that the IV has had no effect, but in fact, it has come from the alternative distribution. In this case, we've made a type 2 error, the probability of which is beta. Yeah? And beta is affected, as you can imagine, by how far apart these two distributions are. So the bigger our effect, the smaller beta will be. The smaller our effect, the bigger beta will be. And what we're trying to do in our experimental designs is actually find a significant difference when one truly does exist. So we want to find that our IV has had an effect and be able to reject our null hypothesis when in fact that is the true scenario. And the probability of that is power. And power is 1 minus beta, the probability of not picking up that effect. Little reminder about confidence intervals. So we can calculate confidence intervals around our sample mean. So confidence intervals are the points between which we are 95% sure our true population mean fits. So if our null hypothesis mean fits between those confidence intervals, yeah, we would retain the null hypothesis. If it doesn't fit between those confidence intervals, we can reject our null hypothesis. And the confidence intervals based on an infinite number of samples from the same population will all be slightly different. But you can see the majority of them will contain that population mean fitting between those points. So let's move on now just to remind ourselves about t-tests. We'll start off with a simple single sample t-test. So what our t-test is based on is the observed difference over our expected difference. That is, how far our sample mean is away from the population mean in terms of the standard error of that comparison distribution. Okay, so let's go back to a simple single sample t-test to remind ourselves of this hypothesis testing procedure. So in a single sample t-test or in any t-test, what we're looking to do is compare the variance that's due to the observed difference between our means, or in this case between our mean and the population mean, in terms of the expected difference. That is the amount of difference we'd expect there just due to sampling error. And how we do this in a single sample t-test is we take our sample mean away from our population mean and we divide it by the standard error of that comparison distribution, the sampling distribution of means. To calculate our standard error, we simply estimate that based on the standard deviation of our sample. We can calculate confidence intervals around our sample mean that we think the population mean would fit between, that we're 95% sure our population from which that sample has been drawn would fit between. And we simply do that by t plus or minus our standard error. Then we need to think about our effect size. How strong or how big is the effect of our DV? Okay, and the way we would usually use this is Cohen's d, and we'll look at a few examples of that later on. And what Cohen's d is simply telling us is how many standard deviations apart are those means that we're comparing. And then the other thing we're interested in, of course, in our tests is our power. What is our probability of finding a significant difference if one really exists? And as I said, effect size is a key aspect of power, as is also sample size. Okay, so let's run a quick example of a single sample t-test. So imagine the Happy School Homeschool Association has come to us and said, we think our homeschool kids have a better reading level through the homeschool program than normal kids going to normal school do. So they've collected data from a sample of 16 homeschool kids and they have a mean reading level of 60. We know that the mean reading level of the Queensland school population is 54. So let's see if the homeschool kids' reading level is significantly higher than the normal school population. So we run our little single sample t-test and we can see that we have a significant t-value, that the mean difference between our homeschool kids and the population is 6. And here we have the confidence intervals of that difference between means. And we can see it goes from 0.4 to 11. So as 0, which would be our null hypothesis mean, that there's no difference between our homeschool kids and our normal school kids, does not fall between those limits, that is another way of hypothesis testing and saying that we're 95% sure that our homeschool kids are reading at a significantly higher level than our normal school kids. So we can reject our null hypothesis and accept our research hypothesis that homeschooling enhances children's reading level. So remember, we have a few assumptions when we are running inferential statistics. First one being the normality assumption. It's an important assumption underlying our t-tests because the sampling distribution of the means follows a normal distribution, and all our probability is based on the fact that it does follow that normal distribution. Now, fortunately, we do have the central limit theorem, which is fundamental to our parametric tests. And according to the central limit theorem, no matter what the shape of the scores in our population, if we draw a large enough sample, the sampling distribution will approximate a normal distribution. But in our example, we only have a very small sample, and so we may not be 100% confident that the central limit theorem will deliver us a perfectly normally distributed sampling distribution. So what can we do if we think our normality assumption has been breached and we're not confident in our normal t-test? So you would have learnt in second year that we can use a non-parametric test, such as a rank order test, such as a Mann-Whitney U test or a Wilcoxian sign test. Or we can use what's called a bootstrap test. So if you've got a strongly skewed distribution or a very small sample, and you are not confident that you've met the normality assumption for normal inferential statistics, you can use a bootstrap test. So what a bootstrapping is it's simply a resampling technique that we can use to estimate the sampling distribution of a particular statistics, for example, the sampling distribution of means. So rather than rely on the central limit theorem and assume that the sampling distribution of the means is normal, what we can actually do is run bootstrapping through SPSS. So what SPSS does is it uses our sample as a representation of the scores in the population and then draws lots and lots and lots and lots of new subsamples from that sample. This sampling is done with replacement. That means that a score that's been sampled once goes back into the pool and can be sampled again. So then SPSS will plot the distribution of means of all these new bootstrapped samples to give us an empirical distribution of sample means that's actually based on our data rather than a theoretical distribution of means based on the central limit theorem. We can then use this new empirical distribution to derive our standard errors and our confidence intervals for our sample means. Quirky thing about bootstrapping, though, is that because it is based on these randomly generated samples, every time you run it, you will get slightly different results. Okay, let's see if that makes more sense when you can see it visually. So let's take a sample of around 16 like we had in our t-test. Okay, there's our sample mean and our standard deviation. Now, what bootstrapping does is, so we resample from that sample. We can resample again from that sample and resample again from that sample. So you can see each one of those resamples is slightly different. And then what's happening when we resample is SPSS is building up a new sampling distribution of the means based on the means of these samples taken from our original sample. Okay, so if we continue taking lots and lots and lots of resamples, you can see it's building up there a sampling distribution of the mean, and look how that sampling distribution is hugging more or less around our original population mean. And keep on resampling, and what SPSS actually does is it does that many, many, many times, okay? And you can see there, it actually then builds up this new empirical distribution. So essentially, if we didn't have the central limit theorem or bootstrapping tests, what we'd actually have to do is take samples of an infinite number from our actual population and plot the actual sample means to get our sampling distribution. But our central limit theorem has done this for us using probability. Okay, and so theoretically it builds up this theoretical sampling distribution of the means. What bootstrapping then does is, based on our single sample, it resamples and makes an empirical distribution that is an estimate of what our sampling distribution would be. So let's have a look now at SPSS and how we run bootstrapping in SPSS. Okay, so we go into our one sample t-test. We actually have a little option here that says bootstrap. So if we click on that, we tick the box that says perform bootstrapping for us, off it will go. Okay, we can actually adjust the number of subsamples that the bootstrapping is based on. Our confidence intervals, we can adjust those, but as we know for the moment, they're normally set at 95% confidence intervals. And we leave it on the simple option, which is the standard. We'll look at stratified options later when we get into more complex designs. Okay, so let's have a look at the output that we get from those bootstrap tests now. Okay, so we get a similar table of descriptives as we did before, but this time we have our bootstrapped confidence intervals for our actual sample mean. So what these are telling us is that we are sure that the population mean falls somewhere between, we're 95% sure it falls somewhere between 54.44 and 65.63. And you can see that 54 mean lays outside of our normally school children, lies outside of that confidence interval. Then we'll just get a straightforward t-test as we did before, and then we'll get bootstrapping for our one sample t-test. So our mean difference remains the same, our t-test itself remains the same, but we get bootstrapped confidence intervals for the difference between those means. And again, we can see that 0, of no difference, our null hypothesis of no difference between our homeschool kids and our normal school kids doesn't fall between those intervals. So we can reject our null hypothesis and accept our research hypothesis that our homeschool kids are doing better on their reading tests. So the last thing I'd just like to leave you with then is to think about effect size. So a significant t-test tells us that there's a difference between the mean for our sample and the population mean derived from the normative sample, but it doesn't tell us how large or important that difference is. So effect size is a measure of the strength of the relationship between our IV, or the measure of how large the effect of our IV actually is. So Cohen's d is the best measure of effect size for our t-tests. It is a descriptive measure that's based on our means and our standard deviations of our samples. So it is simply how far apart our means are in terms of standard deviation. So in our example, the mean for our normative population and our homeschool population, our homeschool population was 60 and our normal population was 54. And our standard deviation from our sample is 10.44, giving us an effect size of 0.576. So these two distributions of scores are 0.576 standard deviations apart, and according to Cohen's conventions, that's a medium effect size. Let's have a look here. Cohen's effect size shows that a small effect is around 0.2, a medium effect is around 0.5, and a large effect is around 0.8. Okay, moving on to independent groups t-test now, where we've got two samples that we want to compare. So we'll have population 1 with a sampling distribution of means, population 2 with a sampling distribution of means, and then we have this new comparison distribution, which is the sampling distribution of the difference between means. And this is our comparison distribution for our independent groups t-test. Okay, so the underlying logic of an independent group's t-test is exactly the same as for the single sample t-test. We're still looking at our observed difference over what we would expect to find just due to random individual differences. But this time our t-test looks like this. We have mean of sample 1 minus the mean of sample 2, and this time we're dividing it by the standard error of the difference between two means. That is the standard deviation of that new comparison distribution, the sampling distribution of the difference between means. And degrees of freedom in this case now becomes n minus 2 because we have two samples. So let's look at a quick example. So this is based on a study by Bushman, who conducted an experiment on the effects of watching violent television on the accessibility of violent constructs in memory. So essentially he got 200 undergrad psychology students and got them to watch 15 minutes of either a violent movie or a non-violent movie, and then gave them a free association test. In which they were given a list comprising 26 homonyms. Each of one had a potentially aggressive meaning. So the data shows us the mean number of aggressive free associates generated within each condition. And we can see in the violent condition there were 7, and in the non-violent condition there was a mean of 5. So we run that little data set in SPSS, and this is what we get. So we get our group statistics. So let's have a look at it without bootstrapping, and we just get the number of people in each sample, the mean for each sample, the standard deviation, and the standard error of the mean for each one of those sampling distributions, for each one of those samples. If we got SPSS to bootstrap for us, it would give us the 95% confidence intervals for each one of those sampling means. Then let's run our t-test. So the first test that we see in the table is our Levine's test for equality. This is our test for homogeneity of variance, another one of the important assumptions underlying our t-test. And what we want is a non-significant Levine's. We don't want there to be a significant difference in the variance in each of those samples. And if we have a non-significant Levine's, we can assume that our homogeneity of variance assumption has not been breached. Then let's have a look at our output. We have our mean difference, yes, between our groups, and we have our confidence intervals of that mean, around that mean difference. And again, remember, if 0 doesn't fall within those confidence intervals, we can say that those samples have indeed come from different populations, where there is a difference between people who've been exposed to violent movies and those not exposed to violent movies. Our bootstrapped output looks pretty much identical, except that what we have now is our bootstrapped confidence intervals for the difference between those means. You can also see here that we have two lines, one where Levine's has not been breached and one in the case of Levine's being breached and our homogeneity assumption not being intact. Just the last note, effect size. So from SPSS output, we've got our means and our standard deviations from each group. SPSS doesn't calculate Cohen's d for you, but you can do so easily yourself. So our effect size is the difference between our means over our standard deviation, or our S pooled in this case, because we now have two samples. We can easily calculate our S pooled, or our standard deviation for that combined sample, by pooling the standard deviations from each one of our samples. So we take the standard deviation of sample 1 and square it, the standard deviation of sample 2 and square it, and divide it by 2. That will give us our S squared pooled. If we take the square root of that, that will give us the estimated standard deviation from both of those samples. We then simply put in the difference between our the means of our two conditions, divide it by our estimated pooled standard deviation, and that will give us our effect size. So we can see there it's 0.4, so it's somewhere between a small approaching a medium effect size. And there it is. You had t-tests in a nutshell.